Hello everyone, my name is Nicole Marks, and today I'll be giving a technical presentation on the salt and metal inputs to a rural to urban watershed. This work is the culmination of my Master of Science in Environmental Science thesis work at Villanova University, where I worked with Dr. Stephen Goldsmith. I have since graduated and am now working as a NOAA Coastal Management Fellow based out of the Delaware Department of Natural Resources and Environmental Control. First, I'm going to give you some background on road salt applications and associated implications. Starting in 1938, we began to apply road salt to roadways in the United States. The reason we apply road salt is for de-icing roadways, sidewalks, parking lots, and other impervious surfaces. Therefore, we chiefly apply the salts in locations with winter weather, such as the northeastern and north-central United States. Road salt works because the sodium and chloride ions interfere with water's ability to bond to form ice. Essentially, it lowers the freezing point of water. It's quite effective and cost efficient, but like a lot of things in this country, we take a good thing and we overdo it. The amount of road salt application has been increasing throughout the northern United States since the first application, as you can see in the graph here. The x-axis represents time, while the y-axis represents millions of metric tons of salt consumption. The most recent years are greater than 20 million metric tons of salt, which is equivalent to 40 billion Morton salt canisters that you probably have in your kitchen at home. That's more than 40 billion of those canisters being applied onto impervious surfaces annually. Since we're applying so much and we know it's running off into streams, we know there will be detrimental impacts. These impacts can be wide-ranging. Of course, salt corrodes automobiles, bridges, pipes, and the roadways themselves. However, we're particularly concerned about the impact on aquatic life. High levels of chloride are toxic to many species of fish and macroinvertebrates. For example, salinity stress inhibits growth and reproduction. High chloride concentrations also disrupt osmoregulation in amphibians. From a chemical perspective, the salt has been shown to drive other reactions in the soil, which also have detrimental impacts on aquatic life and drinking water, but we'll get into that a little bit later. Let's first talk about what we know about salt getting into our streams. Numerous studies have shown the trends that you're seeing in the graph on the right throughout the north central and northeastern United States. Chloride concentration is along the y-axis, while date is along the x-axis. The plot shows increasing chloride concentrations throughout time in the stream near a highway in New Hampshire, while the forested reference stream is not experiencing an increase in chloride concentrations. Many other freshwater bodies across the United States are experiencing similar increases in chloride concentration and salinization. It follows that if you have more impervious surface coverage in a watershed, like the stream near the highway, you'll likely see higher chloride concentrations in streams. So there's several things that are worth noting on the displayed graph. So first, the chloride is on the y-axis, while percent impervious surface coverage is on the x-axis. So the first thing is that the red line represents the New England streams and has the greatest degree of increasing chloride concentration with increasing proportion of impervious surface coverage. The Mid-Atlantic blue line still shows increasing chloride concentrations with the impervious surface coverage, but not with quite as steep a slope as the New England streams line. The Southeast streams green line has roughly a slope of 0, which makes sense with respect to southern climate and land use. So therefore, if you're further north in an area with a high proportion of impervious surface coverage, chloride concentrations are going to be higher. More recently, others have documented that other ion concentrations are also increasing in freshwater systems. As you can see in the graph, the y-axis is concentration while the x-axis is year. This 2017 study found that especially sodium and magnesium concentrations have been increasing across the United States over time. In Maryland, which is represented in the bottom graph, calcium concentrations have also increased slightly. So the question is, why? Sodium, magnesium, and calcium salts are all used for de-icing purposes. This brings us to the freshwater salinization syndrome itself. In 2017, there was an emergence of interest in the term freshwater salinization syndrome. The freshwater salinization syndrome is a watershed scale increase in salinity and base cation delivery over time. In the northeastern United States, the increases in chloride concentrations with impervious surface coverage, coupled with increased base cation concentrations, is indicative that the freshwater salinization syndrome is occurring. There are many human activities within watersheds that could be responsible for increasing ion concentrations. However, what appears to be a significant driver is the influx of sodium into soils. As you can see in this diagram, the sodium from overland flow displaces other soil-bound cations who are liberated into the groundwater and then released into baseflow. As a result, you're increasing the weathering of soils in these areas. So we're not only increasing salinity, but also base cation concentrations. This freshwater salinization-driven process of cation exchange also extends to metal release in soils. The Wilhelm paper published last year was the first to show salt liberating trace metals from soils into groundwater as baseflow. As you can see in this graph, the y-axis is copper concentration and the x-axis is sodium or chloride concentration. As the sodium and chloride concentrations are increasing, so are copper concentrations during baseflow months. However, this is the extent that we know about the inputs of salts in watersheds and corresponding increases in cations and metals. The studies I've shown you are limited by one of a few things. So first, some of them have an extremely large sampling area, greater than 500 square kilometers. The map here that you see here is an example of that. It's a map of connectivity measurements in the study area of the Kaschau 2018 paper, which essentially defines the freshwater salinization syndrome. Other studies focus on a small headwater stream ecosystem, but realistically, the world operates in between these two spatial scales. Other studies also have a lack of continuous temporal data. So this leads me to my first main research question. What are the impacts of road salt application on the water chemistry of a rural to urban watershed? So, second, one of the things I also wanted to examine is if the salinization syndrome is occurring, is there anything that can help ameliorate the effects? One solution that has been proven to eliminate other contaminants in the past are riparian buffers. Riparian buffer zones are defined as vegetated strips of land located directly alongside freshwater bodies. They are well known for their pollution uptake and storage potential and are frequently used as a stream water quality restoration technique. However, there is some debate regarding the effectiveness of riparian zones, both in terms of buffer width and in comparison to overall catchment reduction potential. A literature review by Sweeney and Newbold attempted to isolate ideal buffer widths for different contaminants. For example, this graph displays sediment removal along the y-axis and buffer width along the x-axis. By finding the region of the curve where it begins to flatten, they identified 30 meters as the optimal riparian width for removing sediment. They also identified 40 meters as the optimal riparian width to remove the majority of nitrate contamination. However, it's unknown how riparian buffers affect the freshwater salinization syndrome. While riparian buffers have been proven effective for nutrients and sediment, their efficacy for removing salts remains largely unresolved. What little data exists suggests that they don't matter. What I mean by that is that development within a defined buffer zone of the stream was less of a predictor of chloride concentration than land use in the entire upstream area, the entire watershed. Therefore, I want to see if this trend holds true with my entire study watershed, which leads me to my second research question. Are land use practices within a stream buffer width a better predictor of contamination than land use practices for the entire upstream area? So, now that we know my primary research questions, let's get into an overview of my study watershed. I'm examining the east branch of the Brandywine Creek watershed. It's a rural to urban watershed in southeastern Pennsylvania, located on the outer fringe of Philadelphian suburban development. The east branch of the Brandywine flows into the Christiana River and ultimately into the Delaware River. So before going forward, I want to share the reasons why I chose this watershed. First, the watershed has a relatively uniform geology. As you can see from this map, the watershed is primarily crystalline rock with a small band of carbonate rock that passes through the center. It actually passes through Downingtown, the city of Downingtown itself. Therefore, inputs of contaminants above Downingtown should be a function of point or non-point sources of contamination. Second, it has a variation in development intensity and land uses and is likely more reflective of other watersheds within this region. For example, looking at this map of national land cover data, you can see that the headwaters are predominantly characterized as yellow and brown, which represent cultivated crops and pastoral land, and those are interbedded with green, which is representative of forested land. As you make your way downstream, you can see an increase in pinks, reds, and whites, which are representative of an urban development gradient. Before going further, I want to give you an idea of what several of my sites look like. These are 3 of my sub-watersheds that will give you an up-close and personal look at my specific watershed. We will start with the sub-watershed in the center, which is actually Site 4. So this is Site 4, which is Indian Run. The red arrow on the Google Earth image points at the sampling site location. If you look at the dark greens on the map, they represent forested land cover, which is the predominant land cover of this sub-watershed. The lighter green represents either agriculture or lawn coverage. In the photo, you can see the presence of healthy, vegetated riparian buffer. Lastly, there's only 2.1% impervious surface coverage, and that represents the low end of proportion of impervious surface coverage within my study site watersheds. So this is my second most upstream site. Percent impervious coverage is relatively low at this site as well. However, in addition to the visible poor riparian buffer, the stream wraps around to an agricultural field, as you can see in the Google Earth image. On the map, you can see that the site has a very large percentage of agricultural land cover. I sampled the unnamed tributary to Beaver Creek site at a park. So the big difference between this site and the previous 2 is the much higher proportion of red, gray, and black that represent impervious surfaces. These surfaces account for 33% of the total land cover. As you can see, this site also has very poor riparian buffer. Another thing that I need to account for in my upstream areas beyond land use is the presence of point sources and associated potential contaminants from wastewater treatment plants. The Downingtown Municipal Wastewater Treatment Plant shown in the red box has the largest permitted wastewater volume discharge per day of my entire study area. It's able to discharge up to 7.5 million gallons of treated wastewater per day. The remaining wastewater treatment plants' permitted discharge volumes are much smaller and are associated with trailer parks or small residential developments. Accounting for these wastewater treatment plant, otherwise known as NIPD sites, allows me to account for potential point source contamination in the watershed. Lastly, I chose this watershed because we're often reliant on these mixed-use headwater systems for their domestic water supply. Some of the upstream portions of this watershed are already designated as high-quality waters by the Pennsylvania Department of Environmental Protection. So that's the next to highest designation you can have. Along those lines, there are conservation groups interested in maintaining and preserving the quality of the Brandywine, such as the Guardians of the Brandywine, who also graciously helped fund this research. So, how did I go about my study? So first, I designated 13 sampling sites, and I sampled each of these locations monthly over the course of one water year. In this case, that was the water year of October 2018 through September of 2019. In the field, I collected data using the YSI multi-parameter probe measuring stream water conductivity, pH, and water temperature. I collected a series of 5 water bottles in the field. Some of these I filtered in the field, and some were collected raw. I'll talk about the associated analyses in a moment. I also determined the amount of flow at each site on the time and date of collection. The acoustic Doppler current profiler BOAT was used at the majority of sampling locations to collect instantaneous river discharge measurements. That's that orange little boat guy. I did this no less than 5 times at each site and took the average of these values. Fortunately, 3 of the sampling sites were located at USGS gauging stations. Data for these sites was taken from the USGS online database. Upon my return from the field, I used ion chromatography to measure for major element and nutrient concentrations. Using ion spectrophotometry, I measured for phosphate concentrations. And metals were measured using an ICP-MS at Villanova University. Selenium, aluminum, cadmium, cobalt, lead, and uranium all had average concentrations below 0.01 micrograms per liter, or the limit of detection, and they were therefore removed from my analysis. I also have a large geospatial component of my thesis work. I delineated subwatersheds above all 13 of my sampling locations. I then determined relative land use land cover for each of the subwatersheds using 2 separate land cover datasets. The first was a high-resolution Delaware River Basin Project land cover dataset from 2013, and it was at 1 meter spatial resolution, so that's in the top map. This land cover dataset characterizes the upstream areas in terms of impervious surface cover, tree canopy, and low vegetation. The second was the more traditional National Land Cover Database 2016 dataset, which has a 30-meter resolution and breaks down land use land cover by degree of development, forest type, and agricultural versus pastoral land. It's displayed in the bottom map. I analyzed these 2 separate land use datasets for several reasons. First, I wanted to make sure that the analysis results from each separate land cover dataset complemented one another. I also wanted to see if the high-resolution Delaware River Basin dataset analyses would produce higher statistical significance due to the higher resolution. Lastly, I wanted to account for the more specific agricultural land use breakdown provided by the National Land Cover land use dataset. So, to revisit my second research question, I determined land use at the watershed scale as well as within a 200, 100, and 50-meter buffer zone of the stream to determine if there was a relationship with the freshwater salinization syndrome. So, as you can see as an example, the map on the right is a map of the 100-meter riparian buffer zone land use. Lastly, I also determined whether there was a relationship between NIPD's volume, that's the wastewater treatment plant volume discharged, and solute concentrations. A key part of my study is determining how non-point source contaminants are arriving to the water column, whether that's through overland flow or through baseflow. So I'm going to take you through this diagram to define the flow pathways. Overland flow is essentially what it sounds like. During precipitation events, water flows directly off of land and into the water column. Baseflow is water that percolates through soil into the groundwater and is then pumped into surface waters. Baseflow here represents the freshwater salinization syndrome in action. Another part of my methods was determining the relative amount of stream flow that was attributed to surface runoff versus baseflow. To do so, I used the USGS Groundwater Toolbox on my downstreammost site, that's Site 14, where there was the presence of a USGS gauging station and associated discharge data. So this image to the right is an idea of what the program looks like, though obviously it's displaying a different region than what's in my study watershed. I analyzed my data using a variety of techniques and statistical analyses. I started with correlation matrices to determine relationships between solutes. I then progressed to principal component analyses and associated regressions. I also compared samples according to site and sampling time using ANOVA analysis. All statistical analyses were completed using JMP version 14.2. So, We're now going to discuss my results and how they help to answer my first research question, which is, what are the impacts of road salt application on the water chemistry of a rural to urban watershed? So, one thing worth noting to start, as it's probably still fresh in your mind, the 2018 to 2019 water year was quite deviant from typical conditions. In the displayed graph, the y-axis is daily discharge, while the x-axis is day of the year. The orange line represents the past average daily flow. The blue line is the daily flow of my water year. So two trends become immediately apparent. First, there's a substantial difference between the average daily stream flow of the past 50 years and this year's stream flow. There's also a flashy component to the hydrograph. There's just one successive storm after another throughout the course of the water year. Building on that theme, using the USGS Groundwater Toolbox Hydrograph separation tool, I was able to determine the relative base flow component of the total stream flow for the water year 2018 to 2019. Daily base flow is represented by the blue line, while total stream flow, including overland flow and the base flow, is represented by the red line. Overlain are yellow dots which represent my actual sampling dates. Many of my sampling events occurred immediately following rain events, while some sampling events also occurred during baseflow conditions. Before moving forward, I would like to highlight the December sampling month. This month was used for my representative stormflow month, as baseflow only accounted for 66% of the total flow during sampling. I would also like to highlight the September sampling month, which I used as my representative baseflow month, as baseflow accounted for all, or 100%, of the total stream flow. So we know there were substantial variations in flow throughout the year. What did we see in terms of temporal variation? The following plots were made using all of my water data from all sampling sites on all sampling dates. The left chart displays sodium concentration and the right displays chloride concentration on the y-axis. My individual sampling dates are displayed along the x-axis to show temporal variation. As you can see, although sodium and chloride concentrations did not vary significantly by sampling date, there was a bump in concentrations at the February sampling date. The February sampling event occurred several days after a snowfall event, after which daily high temperatures were above 32 degrees Fahrenheit. Therefore, the elevated concentrations are resultant of meltwater through overland flow. The other interesting thing to note is the uniform concentration trend throughout the remainder of the year. This trend has been found in other studies in similar geographic regions and suggests that shallow groundwater has been salinized. The next two ions I want to show you are calcium on the left and bicarbonate on the right. The first thing that differs is that sampling date concentrations are significantly different from one another throughout the course of the year. In these cases, concentrations tended to be lower in winter and spring months and increased throughout the remainder of the year, suggesting a substantial groundwater contribution. The graphs here represent all trace metal concentrations in stream water from all of the sampling dates. Trace metals also had significant temporal variability between sampling intervals. Zinc and copper were relatively low in baseflow months. Meanwhile, chromium concentrations were predominantly low overall, but were relatively higher in baseflow months. Arsenic peaked in November and was lowest in September. The statistical relationship of sodium with copper and zinc during baseflow conditions suggests that soil weathering and/or cation exchange play a major role during the remainder of the year. As previously mentioned, I used the December sampling month as my representative stormflow month and September as my representative baseflow month. I performed a mass balance estimation of runoff and baseflow for the stormflow month for Site 14, which again is my downstreammost site. The purpose of the mass balance estimation is to determine relative contributions of baseflow versus overland flow during storm flow conditions. So basically what that means is how much of the total flow is from groundwater versus how much is from runoff during storm flow conditions. Percent baseflow contributions higher than 50% are labeled in red and indicate that the majority of the contaminant in total flow is sourced from baseflow. Percent baseflow contributions between 30 and 50% are labeled in yellow and indicate that a substantial proportion of the solutes are sourced from baseflow. Solutes labeled in black are less than 30% sourced from baseflow, indicating that runoff or overland flow is the major source of the contaminant. So, what I want to point out here is that even though this is during a storm event, more than 50% of sodium and chloride are sourced from baseflow, suggesting subsurface pathways as a major mode of contaminant delivery. Similarly, a substantial proportion of the total copper and zinc content are sourced from baseflow during the storm event. This points to subsurface delivery mechanisms like the freshwater salinization syndrome. Lastly, chromium and arsenic are predominantly delivered by overland flow during these storm flow conditions. So I then wanted to move on to look into the spatial variability of these contaminants. In addition to temporal variations in water chemistry, significant spatial variations in cation and anion solute concentrations were observed. Here we see significantly different concentrations of sodium and chloride by sampling site. All samples collected throughout the year were used for these graphs. Here we see, contaminant concentration is again on the y-axis, while site number is on the x-axis. Site number increases as you move downstream in the watershed. Sodium and chloride concentrations generally increased while moving downstream. This is along with the proportion of impervious surface cover within the watershed. So essentially, as those sodium and chloride concentrations are increasing, so is the proportion of impervious surface cover. The exception is Site 7, which is called Shimona Creek, and it has an uncharacteristically high proportion of impervious surface coverage within its headwaters. Similar trends of increasing sodium and chloride concentrations with increased impervious surface coverage have been observed in mixed-use watersheds and have been attributed to road salt application. The next two ions I want to show you are calcium on the left and bicarbonate on the right. Calcium and bicarbonate also increase significantly as you move downstream. Interestingly, calcium shows a spike at Site 7, Shimona Creek, while bicarbonate spikes at Site 9. However, this is another tributary with a high proportion of impervious surface coverage, so this makes sense. Similar trends have been observed in mixed-use watersheds and have been attributed to road salt-driven soil and concrete weathering. The significantly variable copper and zinc spatial trends were very similar to one another. Zinc and copper concentration spatial trends were also similar to previously mentioned sodium, chloride, calcium, and bicarbonate spatial trends, with concentrations increasing with increasing impervious surface coverage. These trends suggest cation exchange of sodium for copper and zinc within soils. Although chromium did not vary spatially, arsenic showed significant spatial variance in concentration with higher values in the headwaters region where there's a higher proportion of agricultural land use. This brings us to my research question regarding land cover and the freshwater salinization syndrome. As a reminder, my second research question is the following. Are land use practices within a stream buffer width a better predictor of contamination than land use practices for the entire upstream area? In order to determine the relative ability of riparian buffers at reducing impacts of the freshwater salinization syndrome, principal component analyses, or PCA analyses as I'm going to call them going forward, were performed on baseflow month concentrations and then separately on storm flow month concentrations. Sodium, copper, zinc, chromium, and arsenic were used as the input variables in order to determine the relationship between salt application and metal transport. Chloride was not used in PCA analyses in order to avoid muddling the data, as sodium and chloride were so strongly correlated with one another. First, the Baseflow principal component analysis was run on the representative Baseflow month concentrations. Baseflow PCA analysis identified two principal components that explained approximately 81% of the total variance. The associated eigenvalues are in red in the table. The first Baseflow principal component, which is the PCB1, that shows positive associations between sodium, copper, and zinc. The second principal component, or PCB2, shows positive associations between chromium and arsenic. So then, a completely separate second PCA analysis was performed on the stormflow month concentrations. Stormflow PCA analysis identified two principal components that explained approximately 78% of the total variance. The first stormflow principal component, PCS1, showed positive associations between copper and chromium. The second principal component, PCS2, showed positive associations between stormflow sodium and zinc, and a negative association with arsenic. All identified baseflow and stormflow principal components were then compared to point source effluent volume and land cover types. Principal components were first compared to the wastewater treatment plant total permitted outflow volume per day in order to determine whether or not point sources were a major source of solutes to the east branch of the Brandywine. Upon initial comparison with baseflow principal component 1, which again is the sodium, copper, and zinc, there did appear to be a positive relationship with volume discharged per day. However, the slope estimate was extremely low. Additionally, as you can see in the displayed plot, there were two significant outliers driving this relationship. These points represent the two largest wastewater treatment plants in the study area, and they are behaving differently than the other wastewater treatment plants in the watershed. Upon removing these outliers, the relationship disappeared. It was not significant, and the slope further approached zero. There were no relationships between baseflow principal component 2 or any stormflow principal components in wastewater treatment plant effluent volume. Therefore, wastewater treatment plant effluent volume does not appear to be a significant source of these solutes during any flow conditions. At this point, we were able to move on to impacts of non-point sources of contamination, or land covers. I just want to reiterate that I did use two different types of land cover data for this work. And again, I just wanted to be as precise as possible by using the 1 meter spatial resolution dataset, which is displayed on the right. But I also wanted to verify and expand upon my results using the lower resolution but more in-depth agricultural classifications offered by the National Land Cover Database dataset on the left. After land cover percentages were calculated for the 13 watersheds using both spatial datasets, the buffer analyses were then performed. So, in order to analyze impacts of riparian buffers on the freshwater salinization syndrome and determine whether or not there was an ideal buffer width for reducing impacts, various buffer zone sizes were utilized. Land cover percentages were calculated within a 200, 150 meter buffer zone of the stream system for the 1 meter resolution dataset, and within the 200 and 100 meter buffer zones of the National Land Cover Database dataset. Whole watershed and buffer widths land cover percentages were then compared to the baseflow and stormflow principal components that we were just discussing. So, to discuss significant baseflow relationships first. So first we're doing baseflow. Regression analysis shows a significant relationship between baseflow principal component 1, which again is the sodium, copper, and zinc, and impervious surface cover at the watershed scale. A repetition of this analysis with the NLCD data confirms this link. I want to bring your attention to the data point at the top of the graph, which is associated with the Downingtown wastewater treatment plant. With or without this point, this principal component is a function of land cover, because if you removed this wastewater treatment plant influence site, the relationship would actually improve. This relationship confirms the role of freshwater salinization on metal export. Additionally, the fact that this statistical link with impervious surface cover weakened over each successive decrease in riparian zone width suggests this process may be driven by a regional scale groundwater contamination, which is due, of course, to road salt application. These results run counter to the role riparian buffers have been shown to play in reducing nutrient and sediment loads to streams. Regression analysis shows significant, though not pretty, negative relationships between Baseflow principal component 2, which again is chromium and arsenic, and percent tree canopy at the buffer zone scales, but not at the watershed scale. So essentially, the less tree canopy that you have, the higher the concentrations of chromium and arsenic. A repetition of this analysis with the national land cover data confirms this link. Now, when you look at each of these three graphs, you can see the relationships are not exceedingly robust and appear to be driven by some points. That being said, in order to determine whether they are significantly related, we would need to choose more sites with more variation in tree canopy cover than what my sites have. As the statistical relationship improved with decreasing buffer width, this is suggestive that riparian buffers might have some value at removing arsenic and chromium from shallow groundwater, but more data is going to be necessary to tease out this relationship. What may be present when there is no tree canopy that might be contributing to increased arsenic and chromium concentrations? Another regression analysis using the National Land Cover Database and Principal Component 2 showed a significant, though again, not beautiful relationship with percent cultivated crops. This was very driven by the sampling site with the most cultivated crops in sub-watershed. So therefore, it's possible that historical agricultural practices could be responsible for arsenic and chromium arriving to the east branch of the Brandywine during baseflow conditions. But like my last relationship, I would like to have a much broader range of cultivated crop percentages for comparison in order to definitely say that cultivated crops cause high chromium and arsenic concentrations. So now we're going to go on to the storm flow results. So there was a positive relationship between storm flow principal component 2, which again is the sodium, zinc, and arsenic, and percent impervious cover at the watershed scale, not any of the buffer zones. So this suggests a relationship between sodium and zinc and overland flow, which is running off of impervious surface coverage. Again, the lack of relationships at smaller buffer widths indicates that regional impervious surface coverage is more important than riparian impervious surface coverage in predicting sodium and zinc concentrations. Arsenic, if you remember, was negatively related to impervious cover, indicating that impervious surfaces are not a major source of arsenic to the east branch of the Brandywine Creek. So to the regulatory thresholds and how my samples fell. Only one sample was found to exceed regulatory concentration thresholds. And this was the sample collected from Site 7, which is again Shimona Creek, in February of 2019. It had a chloride concentration in excess of the freshwater criterion concentrations for the protection of aquatic life chronic threshold of 230 milligrams per liter, and was also in exceedance of the drinking water regulation concentration threshold of 250 milligrams per liter. As I previously mentioned, the February sampling event occurred a few days after a snowstorm, with several days in between marked by daily high temperatures above 32 degrees Fahrenheit. Thus, this exceedance was likely attributed to meltwater and stormwater runoff. The lack of exceedances elsewhere could be due to multiple factors. So first, there's the snapshot nature of the sampling, and that essentially just means we're only able to collect data for a moment in time every month, and therefore we do not have continuous data. Therefore, I could have missed other exceedances. Also, the water year was well below normal snowfall, which could potentially lead to less salt application. The general lack of observed exceedances suggests development in the watershed has not yet reached thresholds indicative of chronic stress. However, the positive correlation between sodium and percent impervious surface coverage suggests future development may result in additional exceedances going forward. So, to essentially summarize everything that we've been talking about here today, the strong relationship between sodium and chloride with impervious surface in the upstream areas confirms that salt accumulation in soils and shallow groundwater can occur in rural areas. The sustained contribution of sodium and chloride during baseflow conditions confirms that salinization can affect these small rural to urban watersheds. While only one sample exceeded water quality criteria standards for chloride, results suggest that future development within the East Branch of the Brandywine could lead to increased exceedances of thresholds. I also found that considerable amounts of trace metals can still be delivered through baseflow during stormwater runoff conditions. Additionally, the statistical associations between sodium, copper, and zinc during baseflow conditions suggest that cation exchange in soils leads to a desorption of these metals. Once freed, these metals eventually leach into the groundwater and are discharged to surface waters as baseflow. Therefore, cumulative use of roadway de-icing agents not only results in salinization of freshwater systems, but also in an increased export of select trace metals. Although many organisms do require copper and zinc as a micronutrient, the threshold at which these concentrations become toxic to aquatic species is quite low. While the copper and zinc concentrations in the East Branch of the Brandywine did not exceed their respective regulatory thresholds for any of my collected samples, future freshwater salinization syndrome-driven metal concentration increase could lead to toxicity for aquatic organisms. Findings also suggest that riparian buffers are limited in their effectiveness for reducing trace metal and salt inputs to streams. The strong statistical relationship between baseflow principal component 1, which was of course the sodium, copper, and zinc, and impervious surface cover at the watershed scale rather than any of the riparian buffer's widths suggests that shallow groundwater salinization is occurring at a regional scale. Conversely, the positive relationship between vegetated riparian buffer zones and baseflow principal component 2, which was the arsenic and chromium, suggests a different delivery mechanism for these metals. Therefore, vegetated buffers could be reducing runoff from agricultural lands in the headwaters regions, specifically the cultivated crops. Regardless, the high percentage of chromium and arsenic in runoff suggests overland flow is the primary delivery mechanism for these metals. These results can be used to help guide restoration efforts in the East Branch of the Brandywine watershed and in other mixed-use watersheds. As the freshwater salinization syndrome appears to have a regional signature, watershed managers should be focusing on developmental standards that reduce impervious surface coverage throughout the entire watershed, rather than just within buffer zones of a stream system. Additionally, innovative road salt application techniques and reduction measures are recommended for systems, much like the East Branch of the Brandywine, going forward. So, I want to thank first and foremost my primary thesis advisor, Dr. Stephen Goldsmith, for all of his guidance in the field, the lab, with statistics, and with the writing throughout the duration of this project. It would have been impossible without him. I also want to thank Dr. Charles Cravata and Dr. Peleg Kramer for serving on my advisory committee and again helping me throughout this entire process. I would also like to thank the Goldsmith-Rodriguez Lab Group at Villanova for their support throughout graduate school. Lastly, I would like to thank the Guardians of the Brandywine, the Geological Society of America, the Commercial Real Estate Women of Philadelphia, and the Villanova University Graduate School for providing financial assistance for this project. Thank you all very much for taking the time to watch this presentation. I look forward to receiving your questions during the question and answer session on Tuesday, September 22nd at 4:30 p.m. If you're unable to attend my session, please feel free to contact me at the email listed on the screen. Thank you again. We'll talk to you soon.